C. Oh. Well, I already said C. All right, let's do C. Okay, I already said C, so that's what I said. That's what we'll do. Okay. All right. Today I want to talk Bayesian statistics. So we're not going to do any kind of Monte Carlo stuff today, but I think that's all right. We'll spend today talking Bayesian statistics because I think this is kind of the most important application of Markov chain Monte Carlo, and we need to have a framework for to understand this. Now, I know I covered some Bayesian stuff in 102b in the context of parameter estimation, and here we're still going to do something similar, and so some of this stuff might look very familiar, and I think that's okay. It's okay to review stuff that you already know. And I also want to point out, as far as a textbook goes, let me log in here. Okay, so I've posted a link on CCLE. This link was available in the syllabus, but last time I put the link only in the syllabus. Students had trouble finding the textbook. Okay, but so here it is. It's called Doing Bayesian Data Analysis. It's free for students going to UCLA. It's got puppies on the cover. It's a good book. Okay, I think it's very clear and accessible for undergraduates, and I like the guy. So and then plus each chapter starts with a poem, which is like fun. Okay, little limerick, and so I start. So chapter 2 does kind of like some big picture ideas about Bayesian analysis. Chapter 5 covers Bayes' rule. If you've forgotten stuff, you can go back to chapter 4 if you need to review probability things. But I think you guys have enough background to skip over chapters 3, 4, and probably even 5. But if you want to review 5, that's fine. And then so definitely read chapter 2, and then read chapter 6, and then we'll get into chapter 7 later. But so chapter 2, introduction, credibility, models, and parameters. All of these you can probably sing, but it just says, I just want someone who I can believe in, someone at who will not leave me grieving. Show me a sign that you'll always be true, and I'll be your model of faith and virtue. Okay, so anyway, this is stuff on Bayesian stuff. I love the chapter. I think. Wait, this one. Okay. Well, anyway, all the poems are excellent, by the way. So I love this one. All right, you furtive posterior coy distribution, alluring curvaceous evading solution. Although I can see what you hint at is ample, I'll settle for one representative sample. All right. Okay. Well, thanks for humoring me. But anyway, read the assigned chapters, and that was a bit more suggestive than I expected. Okay. Now that I'm reading it to the class, I thought it was creative when I read it in private, but okay. Anyway, all right. I'll stop talking. Not really. I have to. It's my job to talk. So, all right. Let's talk Bayesian stats. All right. Okay, and our textbook author says Bayesian inference is reallocation of credibility across possibilities. I wrote that wrong in the last thing. Okay, so is a reallocation. Okay, and I kind of reviewed, or we went over the Bayesian paradigm a little bit on Wednesday, but I think it's worth going through again today. And so the idea is you begin with credible possibilities prior to seeing the data. Okay, so you start off with some possibilities, and you say, you know, based on my previous experience or based on what my subjective beliefs, this is what I believe to be possible, and these are kind of, and based on all this, this is kind of the credibility or probability I assign to each of these possibilities, okay? And then you look at your data, all right? And when you look at your data, you assess the likelihood of your data or evidence based on each and all of the probabilities, or of the possibilities. Okay? And then after you assess the likelihood of your data based on these possibilities, you update, you reallocate the credibility or probability of each of those possibilities. Update credibility or probabilities of the possibilities, okay? And we actually operate similar, with a similar framework throughout life, okay? So if you are a detective and you're trying to solve some kind of mystery, and maybe you say you got like 4 persons of interest or four people who could have done the crime, you know, right now these are your 4 possibilities, and you look at the data, the evidence that you have, and based on the evidence you might be able to eliminate certain possibilities or whatever, okay? And so, you know, for example, maybe at the scene of the crime there are some footprints, okay, left behind. And maybe one of your suspects, their feet is much larger than the footprints left at the scene of the crime. So based on that, you say, well, what is the likelihood that we have footprints this size if this person were our suspect, okay? And you'd say, well, it seems quite unlikely to have these footprints, okay? I mean, there's a possibility that they got these funny shoes that leave footprints that are smaller than your, you know, I mean, that's a, but you reassess this and you say, okay, well, based on the data I have, it's very unlikely that this person with big feet would leave these small footprints. And so we update and we say, okay, based on this evidence, maybe we eliminate this person as a suspect or things like that. And you go through and you eliminate the other suspects and you're left with just one person, and you say, all right, based on the evidence we have, you know, I'm pretty sure it's not these people and it's this one, okay? And, you know, what's that Sherlock Holmes quote? You know, once you eliminate the impossible, what's remaining, no matter how improbable, must be whatever we say it is, right? What is it? Must be the truth. Okay. See, these authors are much more eloquent than I. Okay, so here we go, and this is what we're doing for Bayesian statistics. Except, you know, we got math involved. So probably the first and the most, I don't know, the basic but most commonly used model that we use to introduce this subject of kind of Bayesian reasoning is the beta binomial model. Okay, and this is covered in great detail in chapter 6 of our textbook, and so definitely it's required reading for you guys. And today, well, we're not going to take a Monte Carlo approach today, okay? And we'll probably have to do a bit of this, some analytic approach for this in the beginning, and then once we have an understanding of how kind of the analytic approach works for this thing, then we can take the Monte Carlo approach, and then once we get a handle on the Monte Carlo approach for this, then we can bring in other Bayesian models that are not as simple as the beta binomial, but are similar in concept in terms of you start with priors, you look at your data, and you update, and you're left with something in the end, the posterior. All right, so first we got to talk about the binomial distribution, and I hope this part is going to be very much review for you guys. Okay, and so we use the binomial distribution to talk. Basically, the response for a binomial distribution is the number of successes after we do n Bernoulli trials, right? So the response, our x, is the number of successes after we perform n Bernoulli trials. Okay, and a Bernoulli trial is just a coin flip, right? Pretty much a coin flip, or anything that has, only two possible outcomes. Coin flip, the classic Bernoulli is a coin flip, but so there's only two possible outcomes, a success or failure. Possible outcomes. Which, success and failure we generally associate with good or bad, but this is just either something happened or it didn't, okay? Two possible outcomes, success or failure, and then the probability of a success is P. So things like, we flip the coin and the probability it lands heads is 0.5, okay? Or we shoot the basketball, and if we're Steph Curry, probability goes in is like 92% or something, okay? And then if it's me, it's 1%. So whatever it is, you attempt something, and you've got a probability of success and a probability of failure, and so that's what we have. And if we do this n times and we're interested in getting x successes, then the probability mass function, the PMF, is going to be, n choose x, p raised to the x times 1 minus p raised to the n minus x. Okay, and this is the probability of observing x successes after n trials, and each trial has probability p of success. Okay, so that's binomial, and I think we've seen this enough that we feel comfortable with it, right? Okay. So the other part of this is the beta distribution. And for whatever reason, the beta distribution doesn't get as much love in intro stats. So intro stats, you get like the normal and the t and the binomial, maybe Poisson. I don't know what other exponentials. Well, not in your intro stats, usually like your stats 100 or whatever. Okay, but the beta distribution doesn't get much love until we get to a Bayesian course, and then this is the only thing we can talk about. But all right, so let's talk about the beta distribution. And we often, when we introduce this, we use some funny terms, like we say it's the conjugate prior to the binomial, all right? And this is true, and this is often how people will describe what the beta distribution is. But it's not very illuminating, in my opinion, unless you're familiar with all of this stuff. So I like to think of a beta distribution as a distribution over probabilities. Okay, so probability P is defined, must be always be between what numbers? You get some probability, the probability of an event, it's always between 0 and 1, okay? And the beta distribution, being a distribution over probabilities, is defined only on that interval from 0 to 1, okay? So the beta is defined on the interval 0 to 1 only, okay? Maybe these are square brackets. Okay, and the beta distribution will tell you what values of P, the probability, are likely or unlikely. Okay, all right, so I'm going to do this silly example to kind of illustrate what we're talking about here, okay? All right, so let's say I've got this, this bucket here, all right? And your friend has a bag of, I don't know, holiday M&Ms, so there's only red and green, okay? And your friend says, oh, let's play a game, and you being a good sport, you say, all right, okay, I will. And he says, okay, and what he does is he shows you a red M&M, and he puts it in the bucket, and then he shows you a green M&M, and he puts it in the bucket, okay? And then he says, all right, you got to close your eyes, and so you do. And then you just hear him putting in a bunch more M&Ms. You like dumping in M&Ms, but you don't know if he's dumping in all red M&Ms or if he's dumping in all green M&Ms or a good mix of red or green M&Ms. You know, maybe it's like 50-50, maybe it's 80-20. You know, we don't know. Okay, and then so after he dumps in all the M&Ms, you open your eyes, or he says open your eyes, and you do, and then the bucket's not transparent. And he says, okay, guess what proportion of the bucket is green M&Ms? All right. So what do you guess? Or he says, okay, well, what could the proportion of green M&Ms be? What do you think? It could be any value, right? It could be anywhere from, well, maybe not 0 exactly, but it could be, you know, something very, very close to 0 or very, very close to 1, because you have no idea how many M&Ms are in the bucket. Okay, you do know there's at least one red, and you know there's at least one green, but you have no idea what kind of M&Ms were dumped into the bucket. Okay, so before we get to actually look inside the bucket or look at any M&Ms, right now our beliefs about what proportion are green is going to be flat between 0 and 1. Okay, so we've got basically a uniform distribution from 0 to 1, and that will actually be the beta 1-1 distribution. Okay, so let me just write down everything I've said so far just quickly. All right, so we've got we'll put in a red M&M and a green one. Okay, so we put. So you see, one red and one green go in. Okay, you close your eyes. I don't know why closing our eyes is important, but I like the mystery of it. Okay, you close your eyes. Okay, we hear more M&Ms go in. But do not know what kind. And then we are asked, okay, we open eyes, and we are asked, what proportion is green? Okay, and your answer is, I have no idea, and so our probability distribution defined over 0 and 1 will look like this. Basically, all values between 0 and 1 are likely. Zero and 1 are equally likely. So this is the uniform distribution, which is equivalent to the beta 1, 1 distribution. The beta distribution is defined by two parameters. They're called shape parameter alpha and shape parameter beta, or A and B, or whatever, shape parameters 1 and 2. Much like a normal distribution is defined by its mean and standard deviation, or a t-distribution is defined by its degrees of freedom and things like that, the beta distribution is defined by these two shape parameters. And right now, after seeing only one red and one green, any value between 0 and 1 is possible for what proportion exists in the bucket. Okay? Is that all right? Okay, and then we say, all right, well, if you want me to give you a better guess for what proportion is in the bucket, I've got to see some data, all right? And so to keep this proper, we are going to gather data by drawing M&Ms with replacement, okay? So we gather data by drawing M&Ms with replacement. Okay, so that means we pull out an M&M, we look at it, and then we put it back in. Okay, and so let's say we record 10 observations, and what we do is we see. So, we pull one out, we put it back in. We end up seeing 3 green and 7 red. Okay. And so after looking at the data, what proportion of the bucket is green? Okay, we're asked the same question. So after seeing this data, what proportion of the bucket is green? Okay, or what do you believe about P? Okay, so we don't have before we do any kind of math. All right, we'll save the math. Let's just talk a little bit intuitively about this. All right, what do you think is a likely possibility for the proportion that's green in the bucket? What's that? 30%. 30% seems very likely, right? If we drew 10 and 3 of them are green, then it seems like 30% green is going to be a very likely value. Okay. Do you think 40% is possible? 40% also sounds pretty likely. What about 20% green? That also sounds likely. What about, could the bucket be 60% green? It could be, but it doesn't sound to be as likely as, say, 30 or 40% green, right? So, you know, the probability that the bucket is 60% green, it's possible, it's not impossible, okay? I could have just happened to get a little bit unlucky on the drawing of green, but it's within the realm of possibility. Could the bucket be 99% green? It's technically not impossible, right? So we only say probability is 0 if it's truly, truly impossible. And it's not truly impossible. It could be, you know, there could be 99 green M&Ms and only 1 red M&M. And because we sampled with replacement, it's possible that we had this really universe-bending freak coincidence that I drew the red M&M, I put it back and I mixed it up and I happened to draw the red M&M again, and this happened 7 times. It's technically not impossible, but for all intents and purposes, we're going to say that is such an unlikely scenario, we're going to say it's practically 0, okay? And so if we wanted to, you know, let me just kind of list some of this stuff down. So our intuition about the proportion green, here, let me close our poll. So our intuition about the proportion green is that, you know, 30% is very likely, 20% to 40% also likely, 60% is possible but unlikely. Okay, and then, you know, 99% seems, you know, practically impossible. Not 0, but close to 0, okay? And then also the opposite, you know, only 1% green also seems practically impossible, right? There could be 99 red M&Ms and 1 green, and just by some freak coincidence, we happen to draw the green one 3 times, okay? Highly unlikely also seems impossible, okay? Technically not 0, but pretty much 0, okay? And so we might represent the distribution of our beliefs about the proportion that's green with some curve that looks like, this would be 0.3, and we would draw something that looks like this, or something like that, okay? So this is gonna be our curve representing, you know, our distribution of what could be, what am I saying? The distribution of what proportion is green, okay? The probability of drawing a green M&M is something like this, okay? Centered at 0.3 is going to be our max, okay? And this here itself is a beta distribution, okay? The beta distribution would probably have shape parameters 4 and 8. Don't worry about where those numbers are coming from just yet, but something kind of expressing this shape is a beta distribution with just different numbers. Is that okay? And then, okay, and let's say, you know, after this happened, you know, you become obsessed with this game, and you say, you know, I want to see 1,000 observations drawn from the bucket, okay? And So now we draw 1,000 M&Ms with replacement. Okay. From the bucket. All right, and so, and this time our data will be 350 green and 650 red. Okay, so after 1,000, so I guess we draw 990 more. Okay, and all right, and so what is the probability distribution for the proportion that's green? Okay, so we don't have to do any math, but let's just intuitively think. After seeing 1,000 observations drawn from the bucket, what do you think is the proportion that's green in the bucket? Okay, so we're still not sure. There's, our 1,000 observations are still subject to random chance, and we might have, by random chance, drawn too many green M&Ms or too few green M&Ms, okay? But based on our data, what seems to be the most likely value? Most likely value for P would be what? Something around 0.35, okay? And what do you think is like a window of possible values of P? We'd probably say, based on the data I've seen, P can really, I'm only gonna believe that P is some value between 30% and 40%, right? So P being between values between 30 and 40% seem credible, and values outside of that range seem like almost impossible to give the values we've seen, right? And values outside of that seem very unlikely. I mean, is it possible that the proportion that's green is 50%? It's technically not impossible, but that means we would have to get this really, really, really bizarre sample where I happen to get 150 too many reds and 150 too few greens, which seems to be incredibly unlikely, okay? And so what would our resulting distribution here look like? So, if we go from 0 to 1, and halfway is 0.5, and 10, 20, 30, 40, something like this. And so here's 35%, this being 0.3 and this being 0.4. Our resulting distribution would probably look something like this, okay? This is what our distribution would look like, kind of saying that only values between 0.3 and 0.4 are possible, with 0.35 being the most likely. And this is also a beta distribution. Okay, it's probably like a beta, don't worry about these numbers, 351, 651 would be kind of the shape parameters that we would use there, okay? Let's take a look at what the beta PDF looks like, okay? So we're gonna look at the density function, okay? And the density function looks scarier than what it really is, okay? So I go to Wikipedia and I say, what is the beta distribution, okay? This is, it shows you these examples. And, oh, that's go back, please. Oh man, what is happening? Stop. Stop, computer. Okay, this is all I want. All right, so here we've got the PDF is x to the alpha minus 1, 1 minus x to the beta minus 1 divided by the beta function of alpha comma beta, where beta alpha comma beta is equal to gamma of alpha times gamma of beta divided by gamma of alpha plus beta. And then we look up, well, what is this gamma function? And the gamma function is this terrifying thing of the integral from 0 to infinity of x to the z minus 1 times e to the negative x dx, and it feels scary, but I assure you it's not. Okay, so our beta of alpha and beta, the PDF of this is x to the alpha minus 1 times 1 minus x to the beta minus 1 divided by the beta of alpha comma beta, where, you know what, let me write this down here. Beta of alpha comma beta is equal to gamma alpha times gamma beta times gamma of alpha plus beta, okay? And then the gamma function of z is equal to the integral from 0 to infinity of x to the z minus 1 and e to the negative x dx. Okay. If the gamma function seems like you don't need to know what the gamma function is, but the gamma function looks a lot scarier than it really is. It's just basically a continuous version of the factorial function of factorial. So if you do, like if I say, what's 3 factorial, you would tell me it's 3 times 2 times 1, and you'd get 6. And if you do what's 4 factorial, you would do 4 times 3 times 2 times 1, and you say it's 24. And if I say, well, what is 3.5 factorial, you don't have an answer for that, right? So like 3 factorial is 6, and 4 factorial is 24, and 5 factorial is 120. But if I say, what's 3.5 factorial, or what's 4.5 factorial, you don't have an answer there. But you could pretend like drawing a curved line to connect all of these things, and then you would just say like, oh, well, 3.5 has to be somewhere between like 24 and 120, and you get some number. And that's basically what the gamma function is, except we do z minus 1 rather than z. So it's just a continuous version of the factorial. It gets weird when it's negative, but don't worry about it. And then this whole thing is you're just multiplying all of these, basically these factorials together. But really, this entire bottom part, like, don't worry about it, okay? This, do not worry about the denominator. Okay, because this serves its only purpose. It's an important purpose, but its only purpose is to ensure that the integral from 0 to infinity, or 0, in this case 0 to 1, of our function integrates to 1. Okay, because for something to be a probability distribution, it has to integrate to 1. And so this thing in the denominator, its only purpose is to make sure that the function integrates to 1. Okay? Only the numerator is important. The numerator is the important part. And we can just say the beta function, or the beta distribution, PDF, is going to be proportional to x to the alpha minus 1 times 1 minus x to the beta minus 1. Okay, so this is the only part that's really important. And I guess we'll have to wait till Monday to take a look at how we can use this and update it. Okay, let me just show you some curves, because I drew these very ugly curves in my notes, but they approximate what they're supposed to look like. Okay, so here I've got a sequence to kind of go from 0 to 1, and we're going by tiny little increments. And I'm going to calculate the density of the beta distribution, basically the PDF of the beta. I guess I ran out of batteries also. I calculate the PDF of the beta for shape parameters 1 and 1, and then and I store that into B11, and then I look at B48, and that's going to have shape parameters 4 and 8, and then I throw in shape parameters 351 and 651. And so these are supposed to represent kind of our prior, before we look at any observations. We just see one green and one red go in, and we're asked, what proportion is green in the bucket. Okay, and so when we do that, if I just plot S and B, B11, we are given, oops, let me do type equals L. Okay, it's not that interesting. It's a flat line at 1, okay? So that's fine. Let me just, I'm going to 26.5. Okay, just so these fit on the same scale. If I plot, what's the distribution? Here, let me change this. Okay, so let me plot that. And so this is our beta distribution after looking at 10 observations, and 3 of them are green. Okay, and we can see that the max, the peak, is at 0.3. Values between 0.2 and 0.4 are likely, and values like 0.6 are not impossible but less likely, whereas values like 0.8 and like 0.01, those are highly unlikely. Okay, and then if I throw in the curve to represent what kind of the distribution after 1,000 observations, where 350 of them are green, we see a huge spike at 350, and it's so tall that it doesn't even fit in our plot. So I'd have to go to change the extent of our thing, and we get a distribution that looks like this. Okay, and the reason why it's so tall and it goes all the way up to 26, the only reason is because when we integrate it, it needs to integrate to 1. Okay, otherwise it doesn't matter. It could just it's just a spike that's about this wide. Okay, but it needs to integrate to 1, and that's why it's so tall, and that's why we have that kind of thing in there. Okay, we could have other. We can throw in something else if I wanted to say, like, well, what if I had observed 33 green after 100? So we draw 100 M&Ms out of the bucket, and we get 33 that are green. Kind of our beta distribution is a little bit more pointy than the red distribution, not as pointy as the blue, because after 100 observations, we have basically more information to inform what values are possible for what's green, but not so much that we're going to completely eliminate possibilities like 0.25 and things like that after 100. But after 1,000, you can eliminate certain possibilities, because you say it's incredibly unlikely to get 1,000 observations where 350 of them are green if the true proportion is 25% or something like that. And as we gather more data, we can update our beliefs about the proportion that's green or whatever parameter we're looking at based on this. Okay, so this was just kind of a conceptual introduction. We'll look at a little bit of the math next week, and then we'll do a Monte Carlo approach after that. Please be sure to read chapters 2 and chapter 6 from the textbook. Okay. All right, we'll see you guys next week, and well, maybe I'll see some of you guys later on my other class, or even at Data Fest. So have a good weekend.